Okay, so little review. Little review of a couple things here. Okay, these are the two kind of topics that I want to review with this question. This goes back to the 3.1 stuff, and there are assignments up now for 3.1 all the way through 3.3. Now, we haven't talked about 3.2 and 3.3 yet, so don't panic when you see those, but that's what we're going to kind of start to take a look at today. 3.2 is really minor. 3.1 had to do with the definition of extrema, and we were looking at absolute extrema on a closed interval. Okay, now it's been a little while here, so let's kind of get our bearings with that. When we talk about extrema is plural, extremum is singular, what are they? Talk to me about extrema, extremum, etc., etc. What is an extremum?
It's higher.
Okay, good. It's going to be a minimum or a maximum. Good. Good. Okay, now a relative minimum and a relative maximum. What did it start with relative maximum? What is a relative maximum? Say it again. Okay, now that would be absolute. Okay, absolute would be the highest point on an interval. Okay. Absolute minimum would be the lowest point on an interval. Say it again. Okay, they occur at critical points, right? And what do they always look like? What is the shape of an absolute max or a relative maximum? It's a peak. Yeah. All it means is relative to the terrain around it, immediately around it, it's the highest point. That's not to say that there aren't other places on the function, way out there somewhere, where it's not higher. But right around that one area, and that on an interval surrounding that critical number, it's the highest point. So that means it has to be a maximum. So we know relative maximum means peak, right? Relative minimum means valley, right? And we said a couple other things about that. We said this. This is, let's look at the different kinds of shapes we could get, right? What if I had a function like, that? Okay, we can see pretty clearly there that we've got 4 relative extrema on that little section of function there. The critical numbers, can you tell me, this is a rounded, kind of a smooth peak. What's the condition for the critical numbers at a round peak? What about the derivative is happening there?
It's 0.
It's 0, isn't it, right? So that's a place where we have a horizontal tangent line, and that's a place where the derivative equals 0. Same thing right here, right? Okay, and so we know that all relative extrema have to occur at critical numbers, and critical numbers occur at 2 different kinds of places, right? They occur where the derivative equals 0, like that. What's the other place where we can get critical numbers? Where it's undefined. And that's what's happening there and there, right? That makes sense? And why is the derivative undefined there? What's going on that makes the derivative undefined? Cusp. Yeah, or sharp corner. Good. So that's the other place, right? The other place is where the derivative is undefined. Okay? Make sense? Yeah, and we've really just touched the surface with this. I mean, we've just barely even begun to look at this stuff. But we're going to go a lot further with this idea. Remember that all relative extrema have to occur at critical numbers, but not every critical number is necessarily going to yield an extremum, right? We could have something like, for example, I think we drew a picture like this, where we had maybe, like right there, where we have a horizontal tangent, but it never actually turns up on the right side and becomes a valley, right? That's what we call point of inflection. Okay, so sometimes critical numbers will be false alarms, but every extremum has to exist at a critical number. So if we can just locate the critical numbers, then those are the only places that we need to check for relative extrema, right? Okay, so moving on to this example then. This is a good example because it for one thing, it deals with absolute value functions, and those are just notoriously cumbersome and hard to deal with. So if we want to find the extreme values of this function on the interval from -7 to 7, right, we're going to find the absolute extrema. They could only possibly occur at peaks and valleys, relative extrema, right? Or where else? The endpoints, right? Okay, so those are the places we got to check. How do you deal with an absolute value function like this? I mean,
like that one too.
One way, honestly, one way that you'll probably eventually, like if you were doing this in your future engineering jobs or something, if you had a problem like this, you just graph it in your graphic calculator and get them that way. But if we're doing this analytically, absolute value functions are, there's a way to handle them, right? We talked about this a long time ago. Remember, we said that the absolute value of A we can define as a piecewise function. And so whenever you see absolute value functions and you want to do calculus on them or some analysis, you always want to rewrite them as piecewise functions. They're defined, you have different definitions on different intervals, right? So the absolute value of A, whenever A is positive, doesn't do anything, right? It just leaves it alone. On the other hand, when A is negative, the absolute value function makes A positive by multiplying by -1, right? Does that make sense? And then in between, when A equals 0, it has the value of 0, right? So we always want to apply that piecewise definition to absolute value functions. Okay, so what if we take this one now? What's a little bit weird about this one, and this you're going to see one like this on your homework, is that it's got two pieces, or two parts, two separate absolute value functions wrapped together. Right? I've got the absolute value of x minus 2 and the absolute value of x plus 5. So we've got to deal with those separately, and then just add them together. So let's take the first one, the absolute value of x minus 2. And let's rewrite that one, how about?
Okay, thank you.
Now we can, well, you talk to me about that. What is that? If I want to write that as a piecewise function, what's it going to look like? The absolute value of x minus 2 would be just plain old x minus 2 when? Okay, when A, in this case, A is represented by x minus 2, right? So it's going to be equal to just plain old x minus 2 whenever x minus 2 is greater than 0, right?
Yeah.
But we want x is our independent variable, so we want to write that domain in terms of x. So what's the one algebra step we have to do there to write that in terms of x? Yeah, we got to add 2 to both sides, right? And so the condition then, the absolute value of x minus 2 equals x minus 2 whenever x is greater than 2. Okay? It's equal to the opposite of that, negative the quantity x minus 2, whenever x minus 2 is less than 0, which would just be when x is less than 2.
Oh.
Right? Does that make sense? And then the in-between case, it's equal to 0 whenever x equals 2. Right? Okay. Make sense? Okay? So there's that one. Now we got to do the absolute value of x plus 5. It just equals plain old x plus 5 whenever x is greater than what? -5. Everybody see why?
Oh, yeah. Lunch.
Okay, you see why? Because it would be when x plus 5 is greater than 0. If I subtract 5 from both sides. So it appears that, and if you think about what an absolute value function looks like, they're just v's, right? And so we can see that the x value at the vertex of that v has got to be that -5. If I were to graph this thing, doesn't it just look like, let's see, 0, 1, 2, 3, 4, 5, -5, doesn't it just look like that?
Yeah.
Right? Because we know absolute values are v's, this one opens up. Not that we even have to know that, but if you just want to reconcile, why is it turning out like this? Well, that's what the graph is, right? We're just over on this side where the slope is positive. It equals the opposite of x plus 5. Then when x is less than -5, and it equals 0 when x equals -5. Okay, so let me clean that up just a little bit, and we'll push these two pieces together. Okay, so if we take the blue and the pink together, what's that going to give us? Let's see.
What?
What?
It's 2 days. You weren't here Friday.
What did you say? What did you call confused? What did you say that you call confused?
What's the blue and pink together? Like, did you confuse you? You know. Okay, I need to pay attention here. Yeah, dude, right? Whatever counts. Oh, it's so small. Kendall doesn't like that. Kevin likes it big. Actually, I kind of understand it.
Okay.
But I don't understand that.
Oops. Oh, man, are you kidding me?
What's going on?
Brian, when you asked, did you mean like everything, or did you mean like my academical? Oh, academic was 20. I got a 14 off of something else. It was a grade. It was, no, economics.
Oh, see, that's big. Kendall likes that.
Okay, here we go.
No, what were you gonna say?
All right, let's get our attention up here, please. Okay, so now if we want to add these up, because our function was f of x was the absolute value of x minus 2 plus the absolute value of x plus 5. Okay, what's that going to look like?
It's definitely not that. There's no Z's, Kendall.
Okay, what's that going to look like? If I add together piecewise functions,
I have no idea.
what do you think?
Kendall,
Now think about the behavior of the blue function. The blue function is really boring for values bigger than 2. It's just a line, isn't it? For values less than 2, it's also really boring. It's just negative the quantity x minus 2. So it would be 2 minus x, right? Same thing over here. It's the pink function is really boring above -5 and below -5. There's only one place where it's transitioning its behavior. Now, if I add these functions together, it's a little more interesting because now the function is changing behavior as a whole is changing behavior at 2 and at -5, right? Does that make sense? So we know that for values of x, let's start with the low values. For values of x less than -5, the pink function is going to be defined like this, isn't it? Right? How is the blue function going to be defined for values less than -5?
X minus.
It's going to be that, isn't it?
Yeah.
Because the blue function for any value less than 2, it always looks like that,
Wait.
right?
Yeah, I'm seeing it. Okay, so, ready?
Could
Okay.
you just go over it again?
Sure. So let me say that again. let me say that again, of the transitional places, let's look at the two places where either of these functions switches behavior. One switch occurs at -5, and one switch occurs at +2, right? Okay, so let's first deal with the leftmost switch, the least of those two places, -5. Below -5, the pink function has the green behavior. And of course, the blue function has the green behavior, right? Because the blue function doesn't even switch behaviors until clear up at +2, right? So if we wanted to write kind of an overall piecewise function, let's just call it f of x. Well, one behavior is going to be when x is less than -5, we get that plus that, right? We're going to get 2 minus x, if I just distribute that minus sign, plus, if I distribute that minus sign, I get -5 minus x. -5, oh, minus x, yeah. Okay, agreed? And we'll simplify that in a second. Okay, so now we have another transition occurring at +2. So what about values that are in between those two, that are greater than -5 and less than 2? Because that would be the next logical place we'd have to look, isn't it? Right?
Yeah.
So if we pick values where x is greater than -5 and less than 2, now isn't that going to be what's occurring? Well, when x is greater than -5, the pink function is doing that, right?
Yeah.
Okay. For the blue function, when it's greater than -5 but less than 2, isn't it doing that still?
Yeah.
See what I'm saying?
Okay.
And so then what's going on, the purple part of the interval is going to look like 2, whoops, let's do down a little bit. 2 minus x plus that. Right? Now, what about for values greater than 2? Because that's the other place where one of these functions is changing behavior, right? So let's look at that one. When x is greater than 2, that's what the blue function is doing, and that's what the pink function is doing, right? And so we'll take the sum of those two. So we get x minus 2 plus x plus 5. Is that right? Yeah. Okay. And then, of course, what's happening at the values at those in-between places now? Let's go look at the actual in-between places. So at the in-between places, at x equals -5, what's happening? Well, when x equals -5, this one is 0, right? And what's going on over here? When x equals -5, we're going to be less than 2, and so we get just this value right here, wouldn't we? Okay, so just negative, well, we call that just 2 minus x.
Oh, yep, 'cause it's.
And we can actually put a value in there, couldn't we?
Yeah.
Right.
Wait, oh, you put the -5 through the x?
Yeah, because when x is -5, this guy is 0, and this guy is going to be right there.
Okay.
Okay?
Mhm.
Now what about, I'm running out of colors here. Let's see, I guess we'll go gray. When x equals 2, then we get 0 from this side, and that's going to be greater than -5, so we'll be in that part of the domain for that one. Right? So So we would just get 0 plus x plus 5. Okay, now we can simplify that. It's very colorful, isn't it? Okay, we can. So what about up here? When x is greater than 2, what does that add up to? What, 2x plus 3 looks like? Does that make sense?
Oh, yeah.
Okay.
Yeah, absolutely.
2x plus 3, right, when x is greater than 2. What about right here? Let's do this middle one. When x is greater than -5 and less than 2, that's right in here. The x's cancel, and I just get 7. Okay. And then if we look down at this bottom row, we get, what does that give us? Negative 2x minus 3. Everybody agree if I just add up all those terms? When x is less than -5. And the in-between values, when x equals 2, we get 7, right? And when x equals -5, we get 7, right? Okay, make sense? So one thing we could maybe do to make this look a little bit easier is we could just put an equal sign there on those, right? Because we're just including when x is greater than -5, it equals 7. When x is equal to -5, it equals 7. So couldn't we just maybe do that? Right? And when x equals 2, it's 7, just like when it's less than 2. So we could put an equal sign underneath that absolute value bar. Go like that. Make things look a little bit better. Okay? So there's our piecewise function. See what we did? Does that make sense? Okay. And these would get more complicated looking if I had more piecewise or more absolute value functions being added together. But if we kind of review what our thinking was on this, all we did was we broke each separate absolute value function into a piecewise function, and then when we add them up, we have to look at not only the original intervals, but also the intervals in between the turning points, right? So we added, we go, below, above +2, below -5, and then in between -2 or -5 and +2. Okay. Now, if we want to do calculus on this, though, because after all, if we go back, I mean, this, like many of these calculus problems you're finding, they just never die. We're trying to find the extreme values, right? So what we really want to do here is find the critical numbers, okay? Now, the good news is, on a problem like this, a lot of times you could finesse your way through this in hindsight and say, we probably didn't even need to do all that work. We probably could have just kind of thought about it this way and avoided all that work we just did. But first, you got to, in order to get to that point, you got to do the work once or twice.
Somebody's gonna die. Somebody's gonna die.
So if this is our function, if we want to take a derivative, right? Because we said that the critical numbers, right? We're looking for critical numbers. The critical numbers have to occur where the derivative equals 0 or is undefined, right? And then we're just gonna compare the values of the function at the critical numbers to the endpoints to find the absolute extreme. Because the absolute extreme, it could either be peaks or valleys or endpoints, right? So what if we differentiate this? This is kind of strange. You haven't done this really before. Differentiating a piecewise function, all we do is just differentiate each piece separately. So if this is the function, then this is the derivative.
Let's see.
What's the derivative of 2x plus 3? 2. What's the derivative of 7?
0.
0. What's the derivative of -2x minus 3? -2. So look what this function does. Now, let's just analyze this real quick. On these three separate intervals, the function has three separate slopes, right?
Oh.
How about that? So you know it's gonna be going down, horizontal, down, right? Okay. What can you tell me about critical numbers then? Where is this thing? Where is this thing going to potentially have peaks or valleys? Okay, well the endpoints could be the highest or lowest places, but if we know the basic shape of this thing, for values below -5, it's negative, so it's looking something like this, isn't it? It's going down, has a slope of -2 until we get to x equals -5.
Yeah.
Then it levels off.
Yeah.
And the slope is 0 between -5 and +2. So it kind of looks like that.
That's yeah.
Why is it so marked, like?
Why is it like that?
Yeah.
Because piecewise functions are like that. They're
Oh,
linear and then
yeah.
they're v's.
Mhm.
Okay, but we've added up these two v's, and we've created kind of like I don't know how you describe that. A bowl, like a angular bowl,
It's like a
right?
salad bowl.
Okay, now notice that. So if we're trying to find where this thing has its highest and lowest values, well, this is a little bit strange because look, we get this whole interval where the derivative is equal to 0. We got a horizontal line here. Looking at the graph, I mean, what does that mean? Well, it's got how many minima then? I mean, at how many points could you safely say you're standing on the lowest point on this function on the interval between?
Infinite.
Yeah, every single one of those. When you walk along the bottom of this angular bowl, right? When you're walking along the bottom of this thing, your y value is the same everywhere. Sure, it's the lowest it gets, but every one of those points, so all the points on that interval, would constitute minimum. Does that make sense?
Yeah.
Okay. Yeah. Okay. Right. And then where would the maxima be? Well, it looks like in this case, if we look at the graph of this thing, it's going to be at the endpoints, isn't it? Because our original function, we were going between -7 and +7, right? And so we know that, where's our picture here? Oops, gotta go ahead. So this is -5, so -7 would be, well, let's see. -7 is going to be right about there-ish. +7 is going to be clear up here. Well, actually, maybe higher up here then, huh? Right? But we can find out. Because we're not going to just base this on a graph. We're going to base this on that little table. Okay, so we've got all this information. Let me just get rid of this for a moment. Okay, so we know. And this is going to be whenever x is greater than 2. But because our interval stops at +7, we'll go between 2 and 7, right?
Yep, I'm seeing it. Okay.
Okay, because remember our interval, we're only looking between -7 and 7. It's 0, the slope is 0 between -5 and +2, and it's -2 in between, did I get that? Maybe I got that backwards. Did I write that backwards? I think I did. Oh, no, I didn't.
Yeah,
Never
I
mind,
think
I
so.
did, I'm fine.
No, I don't care. You're good.
Right?
-7.
Okay, -7, because that's what our problem said, we're looking on that particular interval, right?
How'd you get those in the right side?
Say it again, how did I get what?
How'd you get those in the right side?
Over here? Because they're the same as these up here, right? We know that the slope is equal to the derivative of 2x plus 3 when x is greater than 2. But really what we wanted to do there was probably write that as x is greater than 2 and less than 7, because the original problem said that's our interval, right? So this thing isn't going to go forever. We're going to cut it off at x equals -7 and x equals +7. Right? Same thing down here. And so now we've got this picture. We can go, let me cut this one more time. So then remember, and it's been a while, but remember this table we drew where we had x,
I don't remember this. I wasn't here that long.
and f prime, right? We're gonna start using this table a lot, so you get used to this. Our interval went from -7 up to +7. And on that interval, how many critical numbers did we get? Well, everything between -5 and +2 gave us a slope of 0, right? So this is really, in a way, this is kind of, it's these kinds of strange ones like this that are almost the hardest to deal with because they're not normal. I mean, you don't usually get a flat horizontal part of a function, right? But we know that between -5 and +2 on that entire interval, the slope is 0, right? Out here to the right, or to the left, I'm sorry, the slope was -2. And out here to the other side, to the right, for values bigger than 2, the slope was 2. Okay. And so if we check the value of the function, right, what we found when we checked the value of the function, it's 7 every place in between, isn't it? Right. What if we check the endpoints? When I plug in +7, what do I get for a value? 14? 17, right? So, does that make sense? If I evaluate, if we go clear out to the left or to the right endpoint, when x is 7, if I plug 7 in for x, I get 2 times 7 plus 3 is 17. So, the value of the function here is 17, so that's an ordered pair. Every place in between here, I could pick a value of 0, for example. Doesn't matter. It's always going to be 7 is the y value. And then if I go way out to the left, and I check the left endpoint, what do I get there? If I plug in -7, get -17?
No, because it would be 14 minus 3, 11.
Oh, you're right. You're right. So it's 11. Yeah. Yeah, good point. Everybody see that? If I plug -7 in, I get +14 minus 3 is 11.
Oh.
Right, right? And so, oops, one more page. Oops, one more page. So how do we interpret that then? Where is the biggest it gets? Right there,
It's at 7.
right? At x equals 7.
That's the extreme.
That's going to be the maximum. That's the absolute maximum. The absolute minimum is shared by all points in between -5 and +2, right? Okay, so straight. That's kind of it is a little bit of an odd one. And once again, our picture just looks like this, but we're cutting it off kind of like right there and right there. So that's the highest point.
Yeah.
Okay, get an idea?
Yeah.
Okay, and you know, again, absolute value functions, everybody hates them. They're just not fun to work with. You'll see, as we start looking at harder functions that are actually curvy, they're easier to deal with in calculus. Because calculus is sort of built to identify those extreme values. And usually there aren't these shared extreme values like this. Okay, so I just want to go through one that was an oddball. The rest of it will be easier, I promise. All right, so, okay, for today.
Oh, no.
The new topic for today is, I can do this in a couple minutes. It's really, really simple. The mean value theorem is one of these existence theorems.
I don't like existence theorem.
An existence theorem in calculus, we've seen these before. Existence theorems are just the ones that say, if this is true and this is true, then this thing has to exist. Okay? What is it saying in this case? If we've got some function f, which meets 2 criteria. It's continuous on some closed interval from A to B. So closed interval just means containing the endpoints. Now think what that says. If it's continuous on a closed interval, what does that mean in terms of me putting my pen on the board to draw this thing?
Doesn't pick it up.
I never pick it up.
Nope.
Right? I put my pen down at x equals a, and I draw the
No, I can't
whole
write
thing
this
up to
down.
x equals b, and my pen never comes off the board, right? So that's what continuous means. Now, what does it mean if it's differentiable on the open interval between those endpoints? No sharp corners. Exactly, right? There's no sharp corners. So now think what that's telling us. I put my pen down at A, and I'm going to draw a smooth curve with no sharp corners up until I get to B. Outside of that interval, we don't care, because we're only talking about that one interval, right? So it might be that at these, at A and at B, maybe I do have sharp corners. But we don't care about that, because we're putting our pen down at A and drawing up to B, right? Combined, they tell us something about the character of the curve. If we combine those two criteria, I think I mentioned this, but it's been a long time ago, and it hasn't been something that we've used a lot. There's a mathematical definition called smoothness that combines those two. So rather than saying both of those things, we could just say F is smooth
I like that. It's a lot simpler.
on the interval from A to B. Okay, because I don't pick my pen up and I don't draw any sharp corners. If those two conditions are met, now this is just logical if you think about this. If those two conditions are met, then what the mean value theorem tells us is there has to exist at least one x value on that interval, maybe multiple x values, where the slope of the tangent line is equal to the slope of the secant line. Okay? Think about that. Does that make sense? Kind of visually, does it make sense? That if I draw the average rate of change, the secant line, the slope between the points at A, f of A, and B, f of B, that if I'm drawing a smooth curve, there has to be some place on there where this tangent line that's kind of wavering, you know, as I start off, it's going to be a steep tangent line. In this case, as I get close to B, it's a negative tangent line. But someplace in there, there has to be at least one place where the tangent line and the secant line are parallel, where they have the same slope, right? So that's all the mean value theorem tells us, is it has to exist, and therefore, if we want to, we can go find it. It's worth looking for because we know it has to exist, right? Think about this in terms of maybe, what if this curve actually meant something? What if we were talking about, for example, speeds? Okay, let's say we're just graphing distance versus time. Okay, and here's what we're going to start off with. The slope of that would just be velocity, wouldn't it? Everybody agree with that?
Yeah.
Change in distance over change in time is velocity. So what if we did something like this? We started off, we accelerated, and we came up to some maximum speed. What is our average rate of change between the starting time and the ending time right there? Well, the average rate of change is this change in total distance over change in total time, right? It's just going to be this secant line. Right? Make sense?
Mm-hmm.
So let's say that we went a mile in 1 minute, right? So our average velocity is 1 mile per minute, 60 miles per hour, okay? What do you suppose is going to describe to me what your speedometer would read from the start of that trip to the end of that trip? It's going to start off, obviously, at 0, okay? What's going to happen for my average speed to be 60 miles per hour over that minute? What's my speedometer going to have to do? It's going to have to get up to 60, but if I ended at 60, would my average speed be 60?
Mm-hmm.
It has to get over 60, doesn't it? Because we start off going slow, right? And so now imagine that there's a car that's got its cruise control on 60 that's going by us the whole way. We have to cross that mile at the same place he does, don't we? Because he's going 60, constant speed is 60, and so he's going to cover 1 mile in 1 minute. Well, when we start off, he's whizzing by us. Aren't we kind of having to catch up to him, and then we cross the finish line at exactly the same time? But our speed would have to be higher, wouldn't it? Because we had to make up that ground. Okay, so we start off with slow speeds. We probably end up with with pretty high speeds. Okay, but wouldn't you agree that somewhere along that journey, our speedometer had to reach 60 at least once?
Yeah.
Doesn't that make sense? Because there's no way that we
Oh,
could have
yeah,
crossed
yeah.
over from 0 up to like 120 or whatever we get up to. There's no way that we ever could have crossed from 0 up to that high speed without going through 60 at least once.
Yeah.
Probably just once, but maybe we kind of did that a little bit, put on the brakes, and probably not, but maybe, right? And so that's what the mean value theorem says. There's got to be some place in there where the average rate of change equaled the instantaneous rate of change. To find them, you just do a little calculus. Here's the kind of problem that you get with those. Something like this. Here's the function. F of x equals 3x squared minus 5x minus 2. We're looking at the closed interval from -1 to 0. And what you're asked to do is first verify the mean value theorem. Is there guaranteed to be some place where the mean value theorem applies? And if so, take the derivative and find it. Well, if this is our function, now we're probably going to run out of time on this one, but we'll get as far as we can. If f of x is 3x squared minus 5x minus 2, is that function continuous on the closed interval from -1 to 0? Are there any places where it would do wacky stuff, where it would blow up or be undefined?
No.
No. And where would those places occur?
It'd be awesome.
Say again, where would those places occur where a function would be, for some reason, undefined? Okay, vertical asymptote. But I mean, in terms of like the behavior, what would have to happen?
Oh, 0 and bottom.
You have to divide by 0, or what's the other one? Even root of a negative number. There's only 2 places where that could happen, and neither one of those is a possibility here, is it? There are no x's in the denominator, right? So we know that we can check off the first criterion. It's continuous. What about differentiable? Well, let's find out. Take the derivative. Oops. F prime of x is what?
6 minus 5.
Minus 5. Okay. So are there any sharp corners?
No.
Are there any places where that derivative would be wacky? No.
No.
All we're doing here is we're applying the same criteria to the derivative that we applied to the function. Now make this connection, because this is a really cool one. The function is differentiable where the derivative is continuous, right? See what I'm saying?
Yeah.
So first we said the function is continuous where the function is continuous. It's differentiable where its derivative is continuous. So all we have to do is apply the same kind of a search. Any place where in the derivative function we have to divide by 0 or take an even root of a negative number, no and no. So we're fine. We know that it meets the criteria of the mean value theorem. So then we know there has to be at least some place on this interval where the value of the derivative equals the slope of the secant line, right? And that's the formula. Isn't that really just saying rise over run? F of b minus f of a, that's just change in y from a to b, right? B minus a is the change in x. So we'll just find it. Here's our derivative. We'll just set that equal to this guy. Okay. Well, what is f of b? A is at -1, or yeah, -1. B is at 0, right? Makes sense? Maybe it's from Eric Goya. Oh, too late. Okay. Yeah. So what is f of b?
Oh, hey, how's it look up there?
So now b is 0, but what's f of b? If I evaluate my function at 0, what do I get back?
2.
-2, right? So f of b is -2 minus, what's f of a? What's f of -1? I plug -1 in. What,
0.
is it 0?
No.
I don't.
No.
I counted it up.
5 and then 8 minus 2, so 6. Okay. Right, does everybody see that?
0.
So there's f of a, there's f of b, right? Over b minus a. 0 minus -1.
Okay.
Okay, all I did was just apply this, right?
Uh-huh.
Yeah.
Wait, is it f of b?
Isn't f of b -2?
Or is it switched?
Oh, did I get them backwards?
Yeah.
I got them backwards. Never mind. Yeah, hang on. You're right. Let me
We
flip this
saw
around.
that. Whoa.
So that should have been
now.
6 minus -2.
Yeah.
No, it'd be the other way around.
It should now. It should be
Then what's
b minus a. It's like a -2.
Yeah, so he had it right the first time.
Oh,
I had it right the first
there's-
time.
there you just labeled them wrong. You labeled it wrong.
That's a B and
Yeah.
that's an A. I
Sorry.
had a, so okay, we'll pick it up from there tomorrow. We'll kind of then we'll go to the lab.
Okay, that's me too.
I focused on
No, you're right. You're right. You.
I was like, oh, that's right. And then I was like,
Yeah.